Alright, time for another draftphysics.com, debatephysics.com, also video presentation. Should be the live style video. I'm doing a response video to a video I haven't played yet by math and science guy, Jason. Used to work for NASA in some capacity. And, I like that he's passionate about physics and wants to teach it and wants people to understand it and all that kind of stuff. But, they're impervious to any arguments about how they really don't have evidence for what they claim to be the truth. Like they've somehow proven everything, and they really have proven just about nothing. Especially when you start talking about entanglement, superposition, dark matter, antimatter. It's all just, the thinnest of reasoning and associations. And most of the experiments are so convoluted and complex that you can't trust any of the assumptions about what they think they're observing. And then they can't even describe them honestly, frankly. This guy knows that the Eddington experiment was a pile of crap. He must know that. I don't think you could work for NASA and not know who Eddington was and not know that the experiment was fringe, as evidence, and that it was never duplicated and that they've never even attempted it from space, we're supposed to believe. Even though there's 400 times better resolution, you can see 400 times better. You don't need an eclipse and it takes 5 minutes. And they've never even tried it. So you got to just say, yeah, these people have no credibility. All right, and they're just obnoxious, and people are just evil. Like this little craphead, the lying Valerie Rousseau craphead. Now people are regurgitating his lies. And he still hasn't retracted the crap he stated. Apparently the guy who was arrested, who has the same name as me, he actually lived in Maine. It was a different state. It just really is just so evil that these assholes can get away with this, making arguments from, I will invade your personal life, and, it's just extortion, frankly, and it's disgusting that they resort to that. But whatever. So all you got is cowards and weasels and evil fucktards. That's physics today. Yeah, right. So bad on them. All I can do is my job, which is to explain why I find their arguments to be incredible, frankly, and not credible, not worthy of much respect. It's flat earth science. It isn't real science, and they know better. They know it isn't well evidenced, and they really should just man up and accept that they shouldn't be preaching what they're preaching on such thin evidence, and they ought to actually, instead of spending billions of dollars on obtuse and strange experiments, they actually took gigantic magnetic coils and moved them from New York to Chicago by going up the Mississippi River. This monstrous, huge thing to do some wacky experiment that who the hell could care? Some muon experiment where you're just saying, yeah, sure, you're measuring something you claim to be measuring. The magnetic moment of a muon or something. What a pile of crap. That they'll spend money on. Will they drop 4 pounds 1 foot and 1 pound 4 feet? Nope. Will they do the Eddington experiment? $500 experiment. Will they do that one? No. But they'll spend billions. Okay. Yeah, moving magnets across the country. Amazing bullshit. Do I need to say more? Okay, so this video is going to be on atoms having color. And I just found it an interesting subject just because I, of course, do not believe a single electron, as drawn by Feynman and all these other people, when they make up some story about how physics works. They say some crap like, you have an electron in an atom, and the electron jumps from one energy level to another one, and a photon flies out. They just draw it with the little squiggly line. These are photons flying out. No, a piece of a photon, not a photon. One of these little humps. Yeah, that's all you could make in an atom. So you can't make a whole photon, because the photon really does hit a gigantic amount of surface. The polarization of a photon, the part that gives it a signature, that it's coming this way, or it's coming this way, or it's coming that way, that's 500 atoms across. Photons are big. Okay, they're made out of little tiny stuff, but their profile is large. So I would argue, just so there isn't any need for a punchline here somewhere, that a photon is really bits, of energy, stuff moving the speed of light. And they have two features. They have a separation in terms of distance, which is their wavelength, and they have a polarization, which is proportional to that distance, and that is their polarization. And so they have, they're moving through space parallel to each other, with a lag, a bit of period, a bit of time between events that will land on the surface. And obviously the events will land on the surface in a sequence, progressively moving forward. And that's why it creates electricity, is because it has a motion. The polarization is really a direction of impacts that's going to push electrons. And the pushing of the electron is electricity. And that's how you got hit by a photon. One that actually can push electricity. Alright, so that's probably enough of that. And so maybe we can start the video now. Maybe. Yeah, I guess we can wait till I feel like it, but yeah, it might take a while.
Hello everybody, welcome back. I'm Jason, and I have a very simple question for you that I really want you to think about.
So what the hell is that a picture of? Who made that pile of crap up?
Does an individual atom, or an individual molecule for that matter, have a color?
And alright, so I don't know what an individual molecule would exactly entail. Is that you're just saying two atoms, or so molecules can get very complicated. So you can have a very large molecule. DNA, for example, very large molecule certainly could have a color, because it's a very large surface made of a lot of different atoms. So I don't know what exactly he's saying here, so we'll have to wait and see.
No, this is not a trick question. If you could actually zoom in all the way in and see an individual atom or an individual molecule, would it actually have color?
So the point I'm making obviously is that it can't, because the individual atom can't produce a photon, can't produce the frequency, can't produce anything. It needs more than one atom has to actually produce the product. You need, just as a photon creates electricity, electricity creates a photon. And electricity is an electron pressure moving from atom to atom. And it needs to move across more than just one atom. Moving across one atom won't produce a photon of any color.
And again, atoms are the smallest building blocks that retain their character, but since they build upon themselves and form molecules, and they're just atoms bonded together, if you could zoom in and see an individual water molecule or an individual...
So again, an individual water molecule is small enough that it probably wouldn't have a color. But again, you get into other molecules that are very large, this whole argument sort of breaks down.
Carbon dioxide molecule, say, or methane, or whatever it is, would that molecule have a color?
and such, and such, and such, and such, and such.
Now, probably your first thought, as is with the case with most people, is of course it has color. That everything has a color, right? But the answer.
Let's see, if I'm just curious how the volume is. I didn't check it ahead of time. And let me look. Turn this on. Should be able to see it from here, maybe. Maybe here. Let's see.
Answer, like everything in quantum mechanics, is not as simple as it first seems.
Probably could turn it down a little bit. Probably. Okay.
All right, now let's take this one step at a time. I want you to imagine a beautiful iridescent butterfly wing shimmering with many, many colors. There are brilliant blues and brilliant greens that dance across the surface, and they're sort of like an engineering
whatever all that is, but okay, fine, get to the
masterpiece of nature, for lack of a better word. But as you zoom in closer and closer, something kind of strange begins to happen. The colors begin to sort of fade and disappear. What's actually going on here? Can we actually see color at the smallest scales of matter?
All right, so obviously for most microscopes you can't, there's no way to get the light to the lens without shining it through the object. And, so now you're, not going to get natural colors. I'm trying to think of what else you could do. But, the simple argument is that, yes, color is bigger than a single atom. A frequency has to be created by more than one atom. That's a photon has to be created by more than one atom. See if he gets to that point and actually says that.
Or is the concept of sort of a deep crimson red or a bright, vibrant yellow or any other color just a macroscopic quality and a macroscopic experience? When you look at textbooks, just flip a chemistry textbook or physics open to some page, you'll eventually see diagrams of atoms and molecules on the page. And
right, now something that large, okay, so, might have enough span for it to be able to create some sort of photon. But it's still way short of 500 atoms.
They're always shown as these colorful little balls, red or yellow or white or whatever it is, and they're connected by little sticks forming the molecule. But is that sort of close to reality or just artistic license? I started thinking about this many, many years ago because back when I was in college, I had...
See, the only way you can see some colors is, through the spectra, but you can only do that when you're starting to break atoms to pieces. And so you're breaking them out of their molecules, and so that's a different function.
Several jobs in laboratories where I
They're clearly got more than one atom is involved.
Used an electron microscope every day. I started out with what's called scanning electron microscope and then moved on to the much more difficult to use transmission electron microscope. So I spent many days in the dark, literally in a dark room with this gigantic machine, very, very expensive, $1 million machine, trying to take pictures of computer chips at the smallest scales. And it got me thinking a long time ago, why are the images only shown in black and white at the highest magnifications?
Because you're not using photons. That's why it's an electron microscope. You're not using photons. You're bouncing electrons off the surface. Because photons stop working.
That we can see. I know you've seen images like this. Just think back to any image from an electron microscope. It might be the head of a fly or the eye or the compound eye of an insect.
And it's also, all that stuff is coated with metal. So, you're basically saying, of course it doesn't have its natural color because you've coated the surface with silver or some other metal. And you're really just looking at a metal plating on the entire surface.
They're always in black and white. Or if you actually do see a color image, you've seen probably color images like that before, it's very obviously false color. It doesn't look real. And
There you go.
you can just tell that it's not what it would actually look like in real life. Now, why is it like that? Why is it either black and white image or some obviously fake color choices? It turns out that it's not just an aesthetic choice. There's actually some really fascinating physics at play here. So what I'd really like to do is start our journey off by understanding why we can't just add color to electron microscope images. Now, I'm going to talk at fair length about electron microscopes here because...
Okay, well, at least you should have titled the video that then. Because that's an interesting subject, frankly, so it's good. It'll be a nice... I haven't watched any electron microscope videos in quite a while. And it's very interesting technology, this whole idea of bouncing electrons off and collecting the bounced ones and making an image out of the bounced electrons. I mean, the principle is quite interesting.
That motivated my original thought process for this question long time ago. And I know that you, watching this, have not ever used an electron microscope. But suffice to say, we're going to talk about it more, but basically, instead of light waves, which were around all the time, an electron microscope uses a beam of electrons to form the image.
Right, so why would you expect color? Duh.
Now, before we get too deep into any of this stuff and try to argue pro or con on any of this stuff, just consider that an electron beam in one of these machines by itself does not have any color. You might say that the rainbow coming from the sun is composed of lots of different colors mixed together. The reds, the violets, all of the stuff you learn about Roy G. Biv and the rainbow, right? But an electron beam has no color. It's not a wavelength of light at all. So when you form an image from a machine...
I just think it's kind of amazing that he's having to explain that electrons aren't photons. Yeah, I think everybody should know that.
Like that, there is no color information right at the outset. So now I'd like to dive a little bit deeper, peel the onion back a little bit more, and try to tackle this question at a deep level. So let's first turn our attention to microscopes in general. You probably used an optical microscope where you put your eyes up to two things and you're using light. So the fundamental limit of what you can actually see with anything, microscope or not microscope, comes down to wavelength. So visible light is a very small part of the electromagnetic spectrum, and it has different wavelengths, about 380 nanometers to 700 nanometers. That's a really small wavelength. And that's physically the distance in space when the wave of the electric and magnetic field that makes up light begins to repeat itself. That's
right. So, and again, that distance is those nanometers. It's just telling you basically, 500. That an atom, the smallest atoms, I guess, are around a half of a nanometer. So you're talking about 1,000 nanometers. 1,000 atoms would fit in 500 nanometers.
What a wavelength is. So our eyes are sensitive to these wavelengths in the visible band, but you already know that there's invisible waves on either side of the visible. There's the infrared, and then there's the ultraviolet. And if you go farther outside of that band, you'll eventually get to radio waves on one side and microwaves and gamma rays.
So he has it. See, this is so funny how they do this with they don't pay any attention to thinking it should be one way or the other. I mean, obviously as a kid, not obvious to me, radio waves were always, on the left over here, and you went higher as you went to the right. So to me it's so unintuitive the way they do this, because you could almost argue that the longer frequencies, it's just slower things should always be at the, there would always be something thought of as something that would have less to it. Just as a frequency, it'd be a lower number, so it should be on the left. Well, anyway, just very unintuitive to me that people would even think of putting the high end on the left and the low end on the right, just completely backwards.
X-rays on the other side, but they're all electromagnetic waves of different wavelengths. The reason I'm going over wavelength here when we're trying to talk about color is because
So now he just did the opposite. You see what I mean? He's just now he switched it the other way around again. So now he has the low frequency on the left and the high frequency on the right, which is right. But you know, it's just so sloppy.
the concept of looking at something, especially when you're magnifying, it puts a hard physical limit on optical microscopes. No matter
I thought it was the Brownian motion that put the limit on optical microscopes. So I don't think he's entirely right. They just move too much. Stuff moves too much to capture it. You know. So I guess it's a combination of those two things. The movement, if the frequency was higher, the movement would matter less. So I guess that's the argument.
how perfect your lenses are, even if you spend $10 billion on amazing lenses, you can't magnify or resolve anything smaller than about half of the wavelength of the light that you're actually using. So that's somewhere around 200 nanometers if you're using an optical microscope.
Right, so that means, 200 atoms, or 300, or 500, but something in that range. 2 to 500 atoms. So you can't see anything smaller than that.
With
As a thing, a clump.
visible light. It puts a limit on how small of an object you can actually look just because you're using light of a fixed wavelength. Now let's try to put this in perspective a little bit. The smallest thing that you can actually clearly see with an optical microscope is about the size of a large bacterium. So you have bacteria that make you sick. You also have viruses that make you sick. Turns out
I don't think that's true. I think you can see a lot of bacteria, so that's, I don't know what the average bacteria size is, but, you can even see like syphilis pretty small with a good microscope. So I don't think that's right.
viruses are much, much smaller, physically smaller than bacteria. So the smallest thing you can see with a really good optical microscope is a large bacteria. Virus, too small for that. You can't resolve it. You can't look at it. If you go inside the virus, you'll get to individual proteins, and then beyond that, individual atoms. They're completely impossible to image with an optical microscope because the wavelength of light that you're using is just enormous compared to what you're trying to focus on.
So again, that's sort of the argument, okay? Instead of him saying, though, that it's way bigger than a single atom. So, there's no way the function of a photon, it has to hit a whole bunch of atoms and cause an effect in all the atoms. It can't just hit one electron and make a photon. You got to hit a bunch of you have to hit more than one, and it has to be across more than one atom. That's the truth of it. There's no such thing as a single atom or a single electron making a photon.
So here's where we have to mix in our brain the concepts that come from classical physics, wave theory, that light...
Get rid of that because that's all wrong. So here he has it switched. So he's used 3 different diagrams and each one is different. So now he's got it back to a low wavelength at the right and a high frequency at the left. Jeez.
Consist of electromagnetic waves, but then we also have to start to bring in quantum mechanics because we know that the
No, we don't. So that's just wooey bullshit.
world really runs.
No, we don't know that. You know that. You think that. And that's all you do. You think it. You don't know it by credible evidence.
And operates on quantum processes. And that means that the light is not really a spread out wave forever and ever. It comes in discrete chunks that we call photons.
So that's the part where I wish Einstein would have said more, because you could interpret Einstein's statements to say that the photon is made out of light quanta, okay, so that the photon is more than one bit of quanta. Or you could interpret it to say that, yes, photons are the quanta. But I don't think that's what Einstein was saying. So I don't think Einstein believed photons were... I think he was saying they're composite objects made of light quanta.
And I'm going to talk in a second about matter, but matter behaves similarly. We think of an electron as a ball, like a little bullet, but it has a wave-like property.
No, it doesn't. So again, it's just made up. There's no, There really isn't any good reason to think, that electron microscope doesn't work on wave theory. It works on clump theory.
Property as well. So it turns out that everything around us has properties of waves, meaning something
No, it doesn't. So again, just more bullshit.
that's oscillating, and also properties of particles, which means it comes in chunks. And so for light, the chunk that it comes in is called a photon. Now,
Right, and so the photon is the sequence of events that moves electrons. Obviously, a single electron can move other electrons. So, but the single electron is obviously much smaller than an atom. So it's a very tiny object, where the photon, because it's a composite made of different pieces, it covers a lot more space. So the electron, although bigger as a single object, is smaller as a functional mechanical machine. Obviously, I'm just saying obviously, the electron is a lot smaller than the atom, and the photon is a lot bigger.
if you think about the wave theory of light, you're going to be limited by the wavelength to magnify. You just can't look at anything smaller than that. What will happen is if you try to look smaller than that bacterium that we talked about, what will happen is the image will get dimmer and dimmer and dimmer. You'll try to focus it. It'll get dimmer and dimmer and dimmer. As you magnify, eventually you can't see anything at all. I want you to imagine being a...
So he didn't really explain why it would get dimmer and dimmer and dimmer, so nothing there.
The beach. A big ocean in front of you. These waves are coming in like parallel wave fronts, and you can think of electromagnetic waves like that.
You could, and it would be really dumb. You can think dinosaurs were just like Barney the dinosaur, and they could dance and goof around. You could think that, but it wouldn't be very smart.
Coming from an antenna somewhere, or from the sun, or whatever it is. And so the waves are coming from the ocean, and they're coming toward you, and they're stretching very, very far horizontally as they come toward you.
No, they aren't. So, there's just no whatever the stretching is. Nothing's stretching. Ugh. Photons are quite discrete and quite consistent. They travel billions of light years without defect.
Now, let's say you put something really large in the ocean right at the beach. Maybe the size of a building. Maybe the size of like 5 buildings. Just kind of like plopped in the water. The waves come and hit the building. What's going to happen is the object is so big compared to the wavelength that the wave, it can bounce off of it and retain its wave character and reflect out back into the ocean.
And why does size have anything to do with that? Every object will do exactly the same thing, so it wouldn't matter how big it is. Any object capable of creating a reflection will create a little reflection. You can have a big reflection or a small reflection. There's no rules here that makes any sense.
You can see this even in the bathtub. If you just kind of like make waves in the water with your hand and then put like a rubber ducky over there.
Oh, brother.
The rubber ducky is similar size to the wavelength. So part of the wave will bounce off the rubber ducky, and as it bounces off, it will retain the wave-like character. And that's what you're...
So none of that makes any sense, right? I mean, every single object, a piece of dust, will, in some respects, reflect some portion of the wave.
Doing when you look at something under a microscope, the light is bouncing off the object and going up through the optics and magnifying it going into your eyes. And you need to maintain the wave-like character in order to go into your eye and trigger, the receptors in your eye to see an image. But now let's say you take the building out of the ocean where the waves are coming, and instead of that, you put a tiny rock in the ocean, or maybe a pebble, maybe just a single grain of sand. Something really tiny compared to the huge wavelengths, the wavelength of the water waves, right?
All right, so this is just making a mess out of the subject. Obviously, if it's smaller than the object, I mean, you can't make electricity without more than one atom. The simple argument is we detect photons by detecting the electricity they create. And that's the simple explanation.
What's going to happen? Is that water wave going to bounce off and reflect back into the ocean? Well, no, because it's so small compared to that spread.
So of course a portion of it will. So again, it's just, and so he's just basically saying that somehow the smaller you go to look at something, less light reflects. Well, that's duh. But that doesn't explain the limitation. The limitation is because of the motion, but whatever.
That wave, what's going to happen is that wave is just going to mow right past it. It's not going to reflect off of it. And even if it did, it would be a tiny splash of water reflecting. It wouldn't maintain its wave-like character.
So there's nothing we could look at that would be that small. So nobody's saying you could put an atom on a slide and look at the atom. You can't. So this is almost silly in terms of its irrelevancy.
So you wouldn't form an image from that if you were looking at the reflected waves. So that's the best analogy I can.
No, it's a terrible analogy because what you're really trying to say is you can't see the texture of the building, that somehow the texture disappears. The wave hits, but you can't see all the convolutions of the building. Something like that would be a better example. It's not that you've made all of the matter disappear, that you've made all of the reflections disappear. It's that the reflections aren't coming straight back, or they're coming back at an angle, or something like that. You could have made some other explanation, but that was just, sorry, no sale.
Can come up with, that's basically why there's a limit to what optical microscopes can look at, because if you're trying to look at anything too small, the wavelength of the light, if you're looking at something smaller than about a half wavelength, it's just not going to reflect and maintain wave-like character.
So again, it doesn't have anything to do with reflect and wave character. Again, it has to do with the fact that the photon is a large object, and a really large object. And so, if you don't have a consistent substance bigger than those sizes, you're not going to see it. You have to shine light on enough mass for the photon to hit the mass that you're shining the light on. The whole photon to hit it.
To form an image in your eyes. And we can talk forever and ever about this. Basically, if you try to look at something too small, which I've done many times with an optical microscope, the image doesn't just get fuzzy or pixelated like on a computer screen. Instead, something called diffraction actually takes over. Diffraction is something you learn about in physics. It's similar to refraction, but different. Basically, the light waves, instead of bouncing off of the object, they essentially bend around. They kind of like bend around, like think of a river forking around.
Says you. They obviously don't hit anything consistent. And so they can't create electricity because they can't hit a consistent surface.
On something. And it basically creates a blurry disk of light called an airy pattern. So it doesn't form an image at all. It just bends around and makes some other pattern that isn't representative of seeing the.
Well, if it's photons, then so it's photons. That means you're agitating electrons, so you're getting back something with a frequency that has to have some color. So if it has a frequency, it has a color. So we're not making a lot of sense. Oh shit! Yeah, I hit the wrong button there.
And bending around the edge of the object. Best example of this, if you could go get an old DVD disc or an old CD disc, those nice and shiny discs, and look at it under bright light, you'll see the rainbow pattern. That's not just reflection, that's something called diffraction, because at the microscopic level on that disc is tiny, tiny grooves that encode the data, and diffraction is happening and interacting with those, so you can see all of those colors. And the smaller the object is you try to look at, or the slit, or whatever it is, the more pronounced this diffraction is, the more spreading or fuzziness, like thinking about the shadow that you.
All right, so again, he brought up slits, and obviously what's happening there is obviously you're just creating a circumstance where all the photons are getting broken, frankly. Because there's no room for the whole photon to get through without it hitting one of the surfaces and having a mess made out of it.
And that's why you can't just keep making microscope lenses better and better, because at some point diffraction will always blur your image into that airy pattern, which looks nothing like the image. It's just some other interaction that the light is happening with the object. But here's the crucial thing. Light consists of lots of different wavelengths of visible light, talking about the visible spectrum. And so when we look at an object all the way up to that optical limit that we can't really go past with optical light, we're able to see color because the waves are interacting with the matter and reflecting off and absorbing some of the wavelengths and reflecting.
So it's again the waves, the waves, the waves, the waves. So it's a frequency and it's a polarization. And the simple argument is either the polarization defines the color or the frequency defines the color. But because the two are proportional to each other, you can't be sure which is which, frankly.
Other wavelengths, and we see what's reflected back. So we're able to see color all the way up until the optical limit of our microscopes, which is about the wavelength of the light you're using. But here's the question for you. What if you try to look at something smaller than that? In the case of what we're talking about today, a molecule or an atom. What happens if you try to look at something that's not only smaller than the wavelength of visible light, but much, 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 much smaller than the wavelength of light? Is there actually color involved in that case?
So that's right, what the video is supposed to be about, and it's 14 minutes into the video before we get the answer. Obviously, you can't even put a single atom in front of, a microscope. So good luck with that.
That's what we're going to focus on next. And this is where the electron microscope comes in, something I use many, many times. Can we see stuff smaller and see it in full color if we're looking at things smaller than light? But before we get started, I want to just talk about something that you can easily gloss over, but it's quite amazing. How can electrons
So he's saying in full color. You can't see anything in full color, so that's absolute nonsense. So, color in, color out.
which are particles, have a wavelength? How can they be used in a microscope? That doesn't seem to make sense in the beginning. I mean, how can electrons be used to focus and make an image of any kind? And this is where quantum mechanics gets a little bit weird, but in my opinion, a little bit wonderful.
Oh, whatever. Mush.
In 1924, a physicist by the name of Louis de Broglie proposed that
Made up bad bullshit, and everybody fell for it for some dopey reason that's beyond my comprehension.
all matter, including electrons, can behave as both particles and waves. And this gave rise to the very famous, in quantum mechanics anyway, concept called wave-particle duality. It's absolutely fundamental to everything you study.
So it's fundamental to nothing, it's essential to nothing. You don't need to believe this crap to understand what a photon is. So it's all just bullshit.
And
Waves are emergent, okay, complex functions. They are not elemental. Nothing can elementally wave.
learn about in quantum theory. You know, it's a little bit unfortunate, and I've been guilty of this myself with my own kids. When you teach
Oh dear. Ew, creepy.
your kids about what everything's made of, you talk about atoms, and you talk about the nucleus, and you talk about the electrons that are little balls that go around the nucleus of the atom. I mean, it's in every textbook. That's what everyone learns. But you really need to erase that from your mind when you kind of get to this level of talking
Well, you probably shouldn't have shown the picture then.
about this stuff, because it's not little balls. And that's all
So it is, okay? It's just that they're not orbiting anything.
about what quantum theory is. Basically, you just have to
They're little magnets, north and south magnetic monopoles. And they are in arrangements that balance their attractive and repulsion. It's that simple.
shake off the concept that there are particle-like things in the universe and that there are wave-like things in the universe. Basically, everything in the universe, whether it's energy or matter, has characteristics of particles and also characteristics of waves.
All right, well, it doesn't. It's just boulders and Sisyphus. Very small, little tiny Sisyphuses and very big boulders. Electrons, protons, and then the bits of force that push them about.
If you don't believe me, that's okay.
Yeah, I don't accept that you've really tested any of this crap.
Hey, I encourage skepticism, but when you study
Oh, no, you don't. So it's silly lies. God, everything you people, again, you have no evidence of anything. You have never proven it takes 25 times the fuel to go 5 times as fast. You just say this shit for 350 years and say everybody should believe you. And then you say, oh, I accept, I'm a skeptic at heart. No, you're not. Clearly you're not.
Quantum theory, there are bajillions of experiments that confirm this to be true, and also quantum theory is one of the most accurate.
I mean, it's just so idiotic to say that. Bajillion of experiments to prove this to be true. That is just an overt, silly lie. It's crazy. And then he's going to point out how this precision experiment, this is the stupid muon experiment, where they transported the magnets to measure the magnetic moment of a muon, and you're supposed to believe that they know what the fuck this is or what the hell they're measuring? Why should you believe any of that crap? That they know what they're measuring? You're not going to see a picture of it, trust me. Okay, it's not going to be diagrammed in any other way, but through their year-long synthesis through the complex filters, they'll put all this data through to come up with their silly answer. But it'll be a silly answer.
Theories to predict and calculate things that we have, so we know we're on the right track.
No, you don't know any of it. You're such horrible liars. These silly exaggerations about what you know, what you've proven with experiment. Disgusting.
With that, the concept of an electron being a ball is not correct. It
says you. It works. It makes perfectly good sense that the charges have to be equal. They have to be playing a line of sight game. They have to be seeing each other. I mean, it's just in so many ways you can know it must be the right answer. They have to have a shape. They have to.
Has some particle character, meaning it can be localized when you measure it, but it also has a wave-like character.
No, it doesn't. No evidence of any waving.
It turns out that all matter has wavelength, but you say,
no, it doesn't.
Wait a minute. You told me waves have wavelength. How can...
No, waves have wavelength. Waves are in medium. There's no medium.
No.
What medium are we waving in?
Electron have the wavelength. Well, I'm trying to tell you that everything around you, whether it's matter, anything you can touch and interact with, whether it's light, photons coming, anything, they all have characteristics of particles, meaning they can be localized in some space, and waves, which means they oscillate in some sort of way.
Right, so the Empire State Building is oscillating in some sort of way. It's just such a pile of crap.
And that's what this physicist, Louis de Broglie, proposed.
And it was crap.
He proposed that everything, electrons, protons, neutrons, other subatomic particles, they have a particle character. We knew that already. But they also have a wave-like character. They
okay, they just keep saying this, whatever this is, and just no... It's just such wooey crap. They're an undefined, this is supposed to be a physics conversation, and there's no physics. There's no physical concept here. There's just this mush. We'll draw two entirely different animals on top of each other. It's like the crocoduck. This is a religious idea that you're going to cram incompatible concepts together. Ah, shit.
The wavelength. So let's review the bidding real quick before we...
No, you didn't do anything. There's no need to review anything. Just get to your fucking point that somehow you're going to make color out of electrons.
We go on because it's kind of critical here. We knew for a long time that light was consisting of a wave-like character. We knew that there was a wavelength. We knew that light waves can interfere with each other. And we know that waves interfere with each other in that way. So we know that light...
Can you see? There's just incessant propaganda. We know. They keep doing it over and over. They keep pushing. And now they're back to left and right again.
Had a wavelength. But then later, when we started doing experiments with matter, something called the photoelectric effect Einstein was involved in, we learned that light not only has a wave character, but it has a particle-like character. That's when we discovered that light not only waves, but it comes in chunks, which is kind of like a particle. So whatever it is, it has characteristics of little bullets, like
All right, so this is just silly because he knows that this isn't even true. Your real argument is that somehow when we're not looking at it, it's waving, and then when we look at it, it's chunking. I mean, it gets ridiculously silly. And looking at it means what? Looking at it with what? Hitting it with what? What do I have to hit it with? Only light from a flash bulb? If there's no flash on the camera, there's no picture? What's your argument? Gravity isn't taking a picture of it all the time?
Particles, but also characteristics of waves, that's undulating and oscillating. That's photons, right? And so for a long time, that was like, okay, that's how light behaves. But we knew that matter was just particles, right? Because
So he's really not going to get anywhere. He's just going to keep doing this over and over and over, just selling this wave part, wave part, wave part, wave part.
we can make beams of electrons, and we can make beams of neutrons, and they bounce off of things. It behaves just like little rocks or little bullets. But then Louis de
He keeps doing it. And then Louis de Broglie, he just told us this happens. And he told us it was antimatter. And then he told us the Grinch stole Christmas. And, of course the Grinch stole Christmas. Everybody knows it's true. It's written in a book. Of course the Grinch did it. This is just so ridiculous. Let's see, I did do some searching, and the older video about mass inertia, and can't find the actual video. Yes, it is gone. It is funny. I did come up with information about the availability of the video, but it's not very helpful. Yeah, I couldn't find it. Yeah, I found references to it, so I know it exists because people reference it, but I can't find the video. Availability. While primarily an archival research, classic PSSSC films are occasionally hosted on institutional repositories or educational archives. Yeah, I know. So they, but it is weird that they exist and then the channel disappears, and then they exist and then the channel disappears. I mean, I don't know whether it's all copyright. I don't know what the problem is, but it seems kind of ridiculous that you can't watch 60-year-old, fucking 70-year-old, 80-year-old videos. The only way to see it is if you are a researcher at MIT, possibly. Well, I suppose I could request it from MIT, but whatever. Not interested in this, whatever it is. Let me just I'll delete you just for the fun of it, because I don't really care about Happy New Yearing. It's very strange why it wouldn't be available. I agree that it does seem strange that it's not available. I'm not saying it means anything besides, they just made some stuff disappear, I guess. But it is just curious because so many of those videos are quite good, frankly. They're, it's pretty good physics for old physics. And, I obviously don't believe in their conclusions about a lot of things, but at least they're not talking about entanglement and superpositions and all that shit. It's a lot better than the modern interpretation. And, they don't think Stern-Gerlach is an experiment where they're shooting something other than atoms. All right, so continuing.
Broglie proposed, maybe matter has characteristics of waves. Then you would know that the photons would have a wave-like and a particle-like character, but then matter would also have a wave-like and a particle-like character. And then you might say, well, wait a minute.
It just makes zero sense. It's just no sense at all. And this whole idea that photons don't have a mass, who invented that rule? Who made that crap up? And what does it have to do with the whole gravity argument? That's another thing with the whole gravity argument. So stupid is because mass doesn't have anything to do with gravity in the sense that all objects move at the same speed in gravity. They're all given the same velocity. So the only question to ask isn't how much mass it has. Just ask the question, how fast is it going? That'll decide how much it's moved by the gravity. So it doesn't even matter whether photons have a mass in the gravity argument, because you don't need a mass to be, in a sense, to calculate how much you're going to be deflected in a gravitational field. The moon and the single atom will be deflected the same amount by a gravitational influence.
If matter, the stuff I'm made of, has a wavelength, a wave-like character, then why don't I notice all of the objects around me having a waviness to them, or maybe interfering with each other? Why does
So what the fuck does this have to do with the title of the video, which was color and seeing atoms, whether they have color or not? Oh, this is such a pile of shit.
doesn't an apple interfere like waves with like an orange when I hit them? Why don't they interfere like waves interfere? Well, it turns out that the formula that governs the wavelength of matter, when you go through it, anything that has a large mass, which any everyday object that we have around you would have a very large mass, is going to have a very small wavelength. And that's why we don't notice it, because everything around you has such an enormous mass that its wavelength is so tiny that if there was any interference happening, it would be all smeared out.
Right, so all of this somehow that mass matters, when the argument is pretty much that in the force realm, like gravity, mass doesn't matter.
And you can never observe it with your eyes. So we observe apples and oranges behaving like balls, but they actually have a wave-like character with a tiny wavelength. And by the way,
So
when I say tiny, I mean incredibly, inconceivably tiny wavelength. And going into a little more detail here for those that are interested, the wavelength of a single electron, a tiny particle, or any other particle, depends on its momentum.
you're right, so you have to figure out what its velocity is, and we just make that up also.
So de Broglie's famous equation, the wavelength is equal to h, Planck's constant, divided by p, the momentum. And as you might remember from classical physics, you can think about momentum involving mass and velocity. So
Right, and so first you have to figure out how much an electron weighs, and they didn't do that using momentum. They did that using 1/2 mv squared. So they don't know how much an electron weighs.
if you increase the momentum, if you make something have higher and higher momentum, the wavelength goes down. But here's the cool part. When we accelerate electrons using higher and higher and higher voltage, they gain more momentum. And so what happens is, because they gain more momentum, when you accelerate an electron beam, then the wavelength gets very small. And remember, the reason we couldn't use optical microscopes is because the wavelength of light wasn't quite small enough to magnify.
And it doesn't have anything, again, to do with the point, because you're just bombarding a surface that you've coated with metal with electrons. And so, yeah, they're going to bounce off the surface. It's going to be that simple.
But if we accelerate a beam of electrons, and if a beam of electrons actually has a wavelength associated with it, then by de Broglie's equation, if we give a beam of electrons a lot of momentum, then we will give it a very small wavelength, and we should be able to look at things much smaller. And that's for an individual electron. The way that we get that small wavelength is by accelerating it really fast.
All right, so you don't have to accelerate really fast to get a small wavelength. So again, that's even garbage. So an electron going really slow is going to have a very small wavelength. So you could certainly do better than optical photons, if that was your only concern, because electrons are so much smaller. Again, an electron to an atom is like an apple to the earth thing. You're talking about an insanely small object.
Get more momentum. Well, look at an everyday macroscopic object. Here's a little remote control I use, for something I have over across the room over here. But there is a lot of mass in this thing. Even when this thing is moving at a very slow speed, it has an enormous amount of momentum because it has so much mass in it. Even if it's not moving near the speed of light, it has an incredible amount of momentum, meaning the wavelength of this macroscopic object, any macroscopic object, is going to have a wavelength so tiny that I'm never going to notice the wave character of this.
Yeah, isn't that convenient? Yeah, you're not going to notice it. Funny.
And if the wavelength is so small, it's just going to look like a particle that bounces off stuff, as we have discussed earlier. So
what if it's not moving at all? Ha 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 ha. So I have a big giant thing and I don't move it at all.
for instance, in a typical electron microscope operating at 100,000 volts, which is typical, the electron wavelength in the beam comes down to about 4 picometers, and that's 200,000 times smaller, in terms of the wavelength.
Right, so why would you need something that much smaller? Why wouldn't you need something just twice as small, or 3 times as small, or 15 times as small, or 25 times as small? Why would you need something 100,000 times smaller? That doesn't make any sense at all, right?
Than visible light. Now, what if you want even better resolution than that? Well, you just crank up the voltage.
So better resolution than that. See, it doesn't make any sense, right? Because we're not going to get better resolution than that. We're not going to go that much smaller. We're never going to see those viruses or any of that crap. So this is just more bullshit he's making up.
Accelerating that electron beam as fast as you can get it. And so modern electron microscopes can operate at several 100,000 volts, producing even shorter wavelengths in the electron beam. And that's exactly what we want. We want short wavelengths, which means we can resolve smaller and smaller and smaller objects. It's kind of...
But you still need to coat the object with metal. So what does this gain you? Because you're not going to be able to coat very small objects.
Like trading a macroscopic ruler that you would use to measure things for a very precise micrometer that you can measure very, very small things with. So here's where the rubber meets the road of where I'm guiding us in this discussion here. I'm asking you the question, does an individual atom or molecule possess the thing that we call color? Does it have a color? So we got to start talking about magnifying things so that we can see it, because if it has color, we should be able to see the color, right? Right? But here's the thing. We can't magnify with visible light with the colors of the rainbow because it's too small. We can't get any kind of image. So what do? We switch instruments to an electron beam, which is accelerated at 200,000 volts, which has a wavelength shorter, much shorter than visible light.
It's like he made this all in pieces and he just keeps being redundant because he made it all in pieces or something.
So we can actually magnify viruses and things much, much smaller all the way down, very, very close to the atomic realm like that. But we're not using a visible light source anymore. So does the object actually possess the concept of color? Well, I'll just show my cards. I argue no. That's an argument. You might disagree with it. I actually want you to leave me a comment. Tell me what you think.
Yeah, so he's just saying it's a yes or no question. I've answered it. And that's as far as it goes. So let's see if it explains why he's saying there's no color. I mean, the obvious answer is because color isn't about necessarily frequency. It's about, again, hitting multiple atoms.
But I think color, what we call color, is a macroscopic thing. It's a thing that we see when the object is much, much bigger than the wavelength of light that can reflect off of it and that we can process with our eyes.
Right, the polarization of the light is too small to hit smaller surfaces. It has to hit a surface as big as the polarization. If it doesn't hit a surface as big as the polarization, it's not going to create a photon, an image that you'll see.
I mean, without the eyes, without any of the reflection, there certainly are electromagnetic waves running around the room. Some of them we call red, some of them we call blue, some of them we call violet. We have different names for the different wavelengths. But we cannot look at atoms with those wavelengths. We can't. If we try to, the interaction doesn't bounce off in the way that we consider to be able to look at something. So when I ask you, does an atom have a color? I'm asking you, can you look at that thing and see color? But if the answer is you can't look at it with visible color, then is there color? Well, it gets into your brain a little bit. I think no. I think if you have to use an electron beam that's accelerated with a wavelength shorter than visible light, that electron beam has no color. It's interacting with the matter. It's bouncing off. It's showing us an image, which is always in black and white for that reason, by the way, on the screen. But by definition, there can't be any color if you're using something smaller than the wavelength of all the colors. And so with these incredible resolutions, electron microscopes can go way down and look at some really cool things. They can image viruses, which are about 100 nano.
Yeah, so I don't know how they do that one exactly. I mean, I thought it would require you to bounce these electrons off, so I don't know what they're bouncing it off of. I mean, I don't think you could coat a virus with metal, so I don't know exactly how it works. I have to look that one up, I guess.
Meters in size. They can even resolve individual protein molecules, which are just a few nanometers across. But what about
I don't think so. Why don't you show us those images?
individual atoms. That's the holy grail. That's what people have been trying to image forever and ever.
No, you can't do that. You can only make that. You can only synthesize that one. You know, that's just complete fakery.
It turns out that even electron microscopes cannot image an individual atom. You might have actually seen images, if you're a nerd like me, that look like images of individual atoms, usually from research labs like IBM or other research labs with lots and lots of equipment that take pictures, so to speak, of individual atoms. But these were not taken with electron microscopes. You don't have the resolution for that. They use something called an atomic force microscope. I have never used an atomic force microscope, but basically, instead of using light or even using a very high electron beam with a high energy, an atomic force microscope, AFM is what it's called, AFM, it works in a really, really weird way. It kind of works like an old school record player, vinyl record player, right? You know, where the needle sits and the thing is spinning and it's kind of bouncing along the surface like that. What happens is there's a very, very sharp tip, and I mean really small tip. And what happens is you scrape it along the surface using a very precise instrument, and it can feel the individual up and down bumps on the surface of whatever it is you're looking at. So it can actually bounce over atoms and build an image like that by detecting the tiny forces, hence the name atomic force microscope, between the tip and the individual atoms underneath. Now, while these images they're genuine representations of the atomic positions. I mean, if you see a benzene ring or something, it'll show you an image of it. It doesn't really show any color because the colors in those famous images that you might have seen.
No, brother. But anyway, yeah, and you're not seeing anything in one unit of time. You're seeing a collective built image
of individual atoms. They're added afterwards to help you visualize that. They're not in the raw data. It's kind of like how you might have seen pictures from an X-ray telescope of the sky, but they have beautiful images. Well, those are beautiful colors. Those colors were added after the fact. X-rays don't carry color either, so it's like false color. It's the same thing with the AFM images of the atoms and molecules you may have seen somewhere. If any color you see was not measured by the instrument, it was added after the fact. And since we're talking about color itself, let's take just a second to go and peel the onion a little bit deeper with color, because it's a little more complex than it first seems, right? When light actually hits an object, there's an interaction between the photon of energy and the matter.
Geez, this is a bit tedious. Very tedious, actually.
There's an interaction there. It doesn't simply bounce off like a tennis ball or golf ball. Instead, the photons are actually usually absorbed by the electrons in the material. I mean, every bit of matter is going to have some kind of like electron cloud around it. So it interacts with the electron cloud, oftentimes being absorbed, briefly exciting them to higher energy states. And then almost instantly, those electrons drop back down into their lower state and they release a new photon.
So they think, okay, it's just another one of those little trivia things, but I mean, they actually think that the electrons in this close to the nucleus are in the low energy state, and they think the ones on the outside are the high energy state. Well, it's exactly the opposite. The ones on the outside are very weakly attached. The ones on the inside are very strongly attached. You need a lot of energy to knock an electron up, okay, out. You know.
And this is why, like an apple appears red. Its molecular structure in the molecules is such that it very efficiently absorbs most wavelengths, but then it re-emits the primary red wavelength if it's a red apple. So the red apple absorbs the greens and the blues and kind of heats up the apple a little bit from that, but then re-radiates the red back to us, and our eyes detect those red.
So it's all re-radiated. The apple's at thermal equilibrium, so it doesn't keep any of it, frankly. It reflects all the light, eventually.
Photons
just doesn't reflect it in the same frequency that it got there.
Using specialized cells called cones in the back of our eye. We have 3 different kinds of cones, and each are sensitive to different wavelengths. Roughly, they correspond to the red color, the green, and the blues. Our brain puts them together into an image. And when light hits those cells, it triggers a cascading chemical reaction that converts the photon energy that hits it into an electrical impulse sent to our brain and interpreted as color. So a lot of what we see out in the world really is happening up here in kind of our interpretation of the raw info coming in. Just to nerd out with you, in the cones there's a molecule called rhodopsin, which changes shape when light hits it. And that change of shape is interpreted by your optic nerve and such. But remarkably, it's actually really cool, our eyes can reset the molecules back to their initial state almost instantly, and that's why we can look and perceive colors constantly without getting tired or wearing out the molecules in the back. However, have you ever looked at a bright color for too long, like a light bulb or something like that? Well, you can temporarily deplete the local supply of that molecule, rhodopsin. It's changing shape and it hasn't reset back, and that causes like an after image. When you look over here, you see like an afterglow of that image until it kind of resets and that molecule changes shape back to its initial configuration. So I've got my opinion. I'm sure you have your opinion. Everybody's got an opinion.
Well, that would be fine if you would have just said about all the things you said. But this is just one thing you're saying. I'm free to have an opinion, but I'm not free to have an opinion about the existence of the wave nature of something and all the other crap you spewed.
It does get a little philosophical when you talk about this. Can you really say that an individual atom has a color, what we call a color?
If an individual electron can create a photon, then you'd have to say yes. So this is the key point, is that whole concept, that whole Feynman drawing bullshit of somehow a photon pops out of a single atom, it's bullshit.
If we can never actually see it in color. It's kind of like asking what color an infinitesimal point is. Well, if the point has no dimensions, can it have a color? And it's true that atoms and molecules can interact with certain wavelengths of light, and in that sense they can have a color associated with them. We just can't form a true color image of any individual atom because of all the reasons we talked.
Yeah, well, the big reason is you just pointed out, but even our own eye requires a whole giant surface, and that's what the cone is created by. It's creating surface area. It needs a bunch of surface to collect photons. It can't collect photons without a lot of surface area. I mean, that's the whole point, is that it's creating extra surface area because photons fall on a big surface.
About here today, even with the most powerful microscopes, the very act of kind of like seeing color requires that our eyes or our instruments or whatever it is we're using to investigate this stuff to capture multiple wavelengths so that we can see which ones are coming back and which ones aren't, reflecting off of the substance. But because of all the stuff we talked about here with the scale of it, then if you can't reflect the colors back to you, then I would argue that it doesn't have the concept of a color down at that scale. Color is a macroscopic thing that you see when there's lots and lots and lots of atoms which can reflect the light. And
there you go. But do you think that's real? I don't think so.
See all of the different colors coming back. Like I say, it's a little philosophical. It reminds me a little bit of that, saying if a tree falls in the forest, but nobody is around to hear it, does it make a sound? Well, most people would say, of course it makes a sound. I mean, nobody...
Yeah, right. Yeah, most people would say this is all bullshit. These fake questions, these false notions, these problems that don't exist.
...is there to hear it. But what is sound? It's kind of the same question. The tree falling would certainly create a pressure disturbance in the air, but that's not sound. That's just a pressure disturbance in the air. When that pressure disturbance hits your ear and vibrates your eardrum, there is an electrical impulse which is interpreted here. That's what you hear as sound. So when the tree falls, it certainly makes a pressure disturbance, but the concept of the cracking and such that you would hear and internalize, I would argue, that doesn't exist if nobody is there. You kind of need the interpreter to hear the sound as well. So the next time you're bored, like me, and you're thumbing through a
Oh, that was a stupid thing to say, actually. I mean, obviously, every piece of it's there except for your eardrum. So what? So you're saying if there's no eardrums, are there sounds? Well, no, I guess there aren't if there's no eardrum to hear it. But to say that mechanically it doesn't exist, that the phenomenon didn't happen, is just silly.
Chemistry book, and you see those colorful ball and stick models showing molecules like methane or carbon dioxide.
Right. Well, they're not showing them their actual colors. They're just showing different molecules. So to make them different colors, so you know these are hydrogens and that these are oxygens and those are nitrogens. They're not colored by any, they're not pretending the molecule is making those colors.
Or whatever, and they're so colorful and beautiful. Just remember, they're representations. They're useful to look at, but they're not literal truth.
Oh yeah, everybody already knew they weren't literally true. Everybody knew that hydrogen wasn't white and oxygen wasn't blue and, whatever.
The reality, in my opinion, is both more complex and more fascinating because at the quantum scale, our everyday concepts break down. Just like
Alright, so they don't, blah, 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 it says you, blah, blah, blah.
electrons having wavelength doesn't make initial sense to us because we don't see any macroscopic object exhibiting wavelength. But it does manifest on a smaller scale.
It says you.
Color manifests on a larger scale. Maybe color doesn't manifest on a smaller scale. It all depends on the scale that we're looking. So the concept of color really breaks down. Now you can get philosophical.
Photons are causing the effect of electricity. That's the thing to understand. And electricity can cause the effect of a photon. So photons can make something, electricity, happen, and electricity can make photons happen. So you understand that a single atom can't be making electricity.
Say it reveals some kind of deeper truth about the nature of matter and light and all that. I tried to be as neutral as I can. I also wanted to tell you my opinion, but what I'd really like to know is what do you think? After hearing all of this stuff, I want to know what you think. Please do drop me a line. I definitely read every comment. I respond to almost all of them, and I'd like to hear what you think. Does it make sense to talk about color of something if we can never actually see it in color?
Well, you blocked me. Yeah.
And as you walk around and ponder all this crazy stuff we talked about today, I want you to remember to always stay curious.
Yeah, just a bunch of crap. Just buy the propaganda, 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 propaganda. And that's all they sell. And such. Alright, so that was more boring than I thought it would be. But, that's life. And such. So I'll do the quickish drawings. Some drawing of some part of the argument to be made about what a photon does when it hits a surface. The interesting part is that all of this stuff interacting between objects, they're all reflections. That there really isn't anything that actually is producing, force. Everything just reflects it. So you could argue that until you actually admit a piece of matter, you can't admit force, which sounds pretty bold. But it's really only through forces can't interact with forces. So two pieces of matter have to interact to create a circumstance where force can be released. So force has to be pushing something like a muon, like an electron gets pushed. Something has to be pushed by force. But the force itself, can't be created any other way than something on a surface pushing into the environment. So you're only going to create high frequency compressions by creating very large distances that you're going to move an electron across inside of an atom. So if you take an electron and move it from the interior out to the exterior aggressively, fast, then you can create a compression in the field, that combined with other compressions in the field will create a photon. Alright, something like that. So the simple argument is that when you run electricity in a wire, and you have a bunch of regularly shaped atoms, look how, they're not very regular. That what's really happening is that you could argue that this is electrons pushing on electrons. So when you squish, this is what you're going to basically do is squish the atom. You're going to push an electron in, and that's going to push the atom. So the atom misshapes for a moment, and that misshaping, okay, moves through cycles. It just goes down. So each atom for a moment, okay, it looks like this, and then a second later it's back to going like this again, and then this one's doing this, and then that one goes back to what it was doing. So it moves, cascades through, but it's not waving, it's just a cascade of pressure. And so what's happening is this electron is pushing out, and when it pushes, it compresses what's coming in. So all the stuff coming in will have its frequency increased. Okay, so that's the color change, be represented by how fast the electrons are moving. So different compounds and substances will move electrons at different speeds and increase or decrease the speed of the photons hitting the surface, creating, I think that's the origin of color anyway. But all it's doing is increasing the frequency, okay, when it's moving out. All right, and the key ingredient, I suppose, is that it goes out, moves out at a faster velocity than it moves back in. All right, and that way it's losing energy to the environment. So if it's compressing photons, moving quicker out, and then slowly back, quick out, slowly back, quick out, slowly back, then it's losing energy to the environment. So that it's increasing these, the frequency of the photons. So the photons coming out will have a higher, on average, frequency than the photons coming in, right? The photons coming in had this higher, this larger frequency, and the photons coming out have the higher frequency. So that's a substance that's losing energy to the environment. And then vice versa would be when it's pushing out slower and it's pushing in faster. So that's the one where the energy of the heat of the universe is higher than the heat of the object. Kind of, you could argue. Heat being measured by frequency in that case. But anyway, so this is basically the electricity. Electricity is saying, just like an antenna, the electricity has to go up the antenna, right? So if I had an antenna, the electricity goes up the antenna, all right, and it goes nearly the speed of light, not quite, but 75% the speed of light, let's say. And it's going to trigger a response. So as these little pulses of electricity go into the antenna, this is going to be happening, this pushing electron thing. So the electron on this surface is going to push out, and then it's going to push out here, and then it's going to push out here, but it's all progressive, right? So by the time this one is this far at the speed of light, and this is going a little bit slower than the speed of light, you can understand that, okay, the next one will be here, and the next one will be here, and that will define the frequency, and that will be entirely defined by how big the atoms are. So whatever size the atoms have between each other will essentially decide what that frequency might be in terms of the distance progressively up the antenna. And that object, okay, that compression is being created through the whole antenna. So essentially it's going to create a bunch of reflections, pushes by the electrons, and those pushes will basically create a compression in frequency that'll be something like this, that'll have a shape to it, where it starts here, down here at the bottom, and then so it's going to go through, this will be the compression. You could argue that it's going to travel through space, and then from here, and so this is the frequency you put in to the antenna, is the separation between these compressions, but they have a shape, so they're going to travel this way, and so, but that's their polarization. So they have to, the receiving antenna has to be in the same alignment for you to be able to see it, because basically you're saying you have an antenna, and you're going to send the thing in between will be going like this between those two. But you can't receive it this way because you don't get the whole signal. You have to be this way so you can get dot, dot, dot. You know, the way the photons are coming. Anyway, so it does explain it. I mean, it does make perfectly good sense. So you're not really sending the force. You're sending the electrons doing this. Because all the electrons going in the wire are actually going into the ground. Right? It's grounded. They're going to be going into the ground. Okay. That's why, you know, you can get burned when you're close to a high powered radio antenna or something, is because there are a bunch of electrons that are flying to ground, trying to get to the ground, essentially. Yeah, I'm just trying to think of how they use antennas in space. Yeah, I'm just trying to think because the electrons won't, yeah, I guess they'll still leave the surface. Yeah, they wouldn't leave the surface. So I guess maybe they don't ever leave the surface. Not enough energy. Oh, that's right. So it's not enough energy for electrons to leave. So you're not degrading the metal. It's not ionizing the metal. So yeah, my mistake. So the electrons are just doing this. They're pushing out and going back, and then pushing out and going back, and then pushing out and going back. And that's the frequency. And all they're doing is creating a compression in the energy that's already hitting them. So it's taking the infrared radiation and all the other kind of radiation that's hitting you, and when you have the electricity going through you, pushing the atoms, then you're going to increase that frequency. And that's why things, when they get hot, start glowing, is because they start pushing on non-visible light and making it visible. So they start turning infrared radiation into visible radiation. So they're increasing the amount of visible radiation by taking the segment of invisible infrared and making it a little higher frequency. So it becomes visible radiation. So it's not actually creating force that's flying out. It's just moving electrons. In most cases, except when you start ejecting them. So when you give them enough energy to expel the electron, okay, then you're likely to be producing X-rays and lots of other stuff along with it, because you're actually pushing the electrons and breaking the atoms. Yeah, how much of that is still? Yeah, I think it's still mostly just. There's some other. You have to accelerate them with some other kind of light or some other kind of photonic, some kind of, like that's why they use radio photons in linear accelerators to push on the electrons. So they hit them with radio photons to push them faster and faster. Yeah. And then they end up creating a bunch of gamma rays and other kinds of radiation in that process. Because I don't think they'd have just electrons. I mean, when you heat something and then create an electrical potential, you're going to move more than just electrons. You're going to move ions. So when they describe an electron gun, you know, it's not really a mechanism that just creates electrons. You know, it's going to create other products that are actually going to be ejected off the surface too. And that's why cathodes and anodes fall apart over time. It's just because you are breaking the atoms on the surfaces. Well, you're breaking them on one side a lot more than the other, frankly. All right. So is there anything else to do with this subject? Probably not. We'll just write this one off as a boring video, I guess. You know, and so what I do want to do is just make compile a list, I guess. You know, I'll make one video because I want to do it for that stupid Jamil guy contest, where I'm not going to propose another theory, but just point out exactly how all the premises of physics are all under-evidenced. And they're embarrassingly weakly evidenced. I mean, you could just keep making arguments about, how you could investigate and say, how could this be credible physics? Like something like the Eddington experiment, that the guy could say in his journal, I got 10% of the data I was hoping for. 10%, it's a huge degree. So you have a very difficult experiment, and you got a 10% data quality. I mean, it's just it's amazingly silly that people who like science don't acknowledge that that's a catastrophic outcome. It just destroys the credibility of any statement regarding what this experiment could prove. Because it's so bad. Why does this camera... yeah, I guess this is your problem. Just gotta find a better holding mechanism, I guess. Sorry. Not your problem. Yeah, it's always a little crooked. Yeah, whatever. Not today. Anyway. Probably have something I could stick in there that'll work. But anyway, alright, till the next time and such and all that kind of stuff. Guess we'll get out of here. I'm tired and distracted. And it's a long weekend and such. That's what I'm looking for. Oh, I'm looking for my mouse, which I dropped. Okay. So, till the next time and such and so forth and whatnot. Blah, 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 blah.